Thank you for joining me today. In today's video, we are going to start talking about chemical solutions. But before we're going to get into that, talking about solutions, we need to discuss probably the most common solvent. And of course, I'll explain what solvent means in a little bit. But we need to discuss the most important and most common of solvents, and that is water. We're going to talk about some of the very unique properties of water. So first off, the large number of hydrogen atoms and oxygen atoms in a sample of water allow for a large number of hydrogen bonds. We'll talk about what a hydrogen bond is in just a few minutes. Water is also a polar molecule. It has a positive side and a negative side. Water is amphoteric. That's a property that says that it can act as both an acid and a base. And we'll talk about acids and bases in a few future videos. The liquid state of water occurs over a very large temperature range. Water has a high specific heat. Now that's a term that we aren't going to use much in chemistry right now, but specific heat is the amount of energy it takes to change the temperature of something. So it takes a lot of energy to change the temperature of water. Water dissolves a variety of compounds. That's why we use it so often when we're dealing with solutions. And it is strong cohesion and adhesion properties. All of this we're going to talk about as we move on in just a bit. But water is also the only compound that I could find that expands when it freezes. There are a few elements that also expand when they freeze, and their solid form is less dense than their liquid form. There's a few elements that fit that, but I couldn't find any compounds that do this. It's very unique in that. Now there might be some others that other people would be aware of. I haven't been able to find any compounds that also are less dense in their solid form than they are in their liquid form. So it's a very important, very cool property of water. So let's talk about these hydrogen bonds. It has to do with hydrogen. That's why it's called a hydrogen bond. But what a hydrogen bond is, it's not really a chemical bond. It's not really a bond between atoms. It's more of an attraction between molecules. And this bond is caused because of the hydrogen atom that is bonded to a highly electronegative atom, like oxygen or nitrogen or fluorine. So when you have hydrogen bonded to oxygen, or hydrogen bonded to nitrogen, or hydrogen bonded to fluorine, highly electronegative elements, you're going to have a very, very polar bond. That highly electronegative element is going to pull the electrons closer to the nucleus or to the electronegative element like oxygen or nitrogen, and leave the electrons off of the hydrogen most of the time. So you've got a very polar bond between the electronegative element and hydrogen, making the hydrogen very positive. Well, when that hydrogen comes in close proximity to atoms that have a lone pair of electrons, which are negative, in their outer shell, or another polar molecule, then you get this hydrogen bond is very much attracted to those lone electrons that are not being shared, but they're in the outer shell of the atom. And so the hydrogen that's very, very positive because of that polar bond is going to be attracted to those lone electrons. And when that happens, you get an attraction that kind of keeps things close together. That's what a hydrogen bond is. In fact, hydrogen bonding is what keeps the double helix of your DNA together. Those nitrogen bases, the A, D, or the A, T, C, and G, the nitrogen bases have nitrogen with hydrogens, and so therefore you have a whole lot of hydrogen bonding. That actually is the rungs of that ladder that's twisted that you learned about in biology. That double helix structure of DNA is held together by hydrogen bonds. So hydrogen bonds are kind of an important thing, but they're a really big part of why water does what it does. So you see here in this picture, the hydrogen bonds are the attraction of the hydrogen atoms to the lone electrons that are on that oxygen side of the water molecule. So those hydrogen bonds give water a lot of the properties that we just talked about, a lot of those unique properties. So let's talk about that. Many of the unique properties of water are because of the large number of hydrogen bonds that occur. Now, a lot of other compounds also have hydrogen bonding because there's a lot of compounds with hydrogen and oxygen, and a lot of compounds with hydrogen and nitrogen. So there's a lot of compounds that have hydrogen bonding, but very few have as much because you have two hydrogens combined with one oxygen. When you have a sample of water, there's hydrogen bonds everywhere. So the large number of hydrogen bonds that occur between water molecules give water a lot of its properties. So it's less dense solid form. Water expands when it freezes. That's because when it's a liquid, the molecules are moving past, and the speed and kinetic energy of those molecules allows them to go past each other without a whole lot of effort. The hydrogen bonding and the attraction that's there is still there, but because the molecules are moving so much more, there's not as much of a grab hold. But as they cool down, as they slow down, those hydrogen bonds start to cause the water to form a structure. And so the hydrogen bonds, you can see in the picture here, the dotted lines are the hydrogen bonds. They force the water molecules to arrange themselves in a very specific arrangement. Well, that arrangement means they're actually going to end up being spread out more than when they're just moving past each other, because they form that little hexagon shape that you see. It's a crystal structure of water, is expansive. And so it takes up more volume when it's frozen than whenever it is a liquid. And so therefore it is less dense. That's what allows water or ice to float. Most all substances, their solid form is going to sink inside their liquid form. So if I have a solid chunk of lead and I stick it into a thing of hot melted lead, that solid chunk of lead is going to sink because the chunk of lead is more dense than the liquid lead. That's not the case with water. With water, when you freeze it, the solid form is less dense because it expands when it is frozen. Water also has a high specific heat. Now again, specific heat is the amount of heat required to change the temperature, all right? Now to change the temperature, you have to increase or change the average kinetic energy of the molecules. So you have to get them moving faster by adding energy to them, or take energy away and get them to move slower. But the average kinetic energy is the temperature. So if you want to change the temperature, you are going to have to break those hydrogen bonds, that attraction between those molecules. Since they are so attractive, it is a lot harder to get those molecules to move past each other and move faster past each other, and therefore it is a lot harder and takes a lot more energy to raise the temperature. Because again, remember what temperature is. It's the average kinetic energy. So it all has to do with how fast the molecules are moving. Water actually has the highest specific heat of any liquid. Now, there are some things that have much higher specific heats than water does. However, those are going to be solids. There are some gases that have pretty high specific heats, but water has the highest specific heat of any liquid. Cohesion is another property of water that is because of these large number of hydrogen bonds. So what is cohesion? It's the attractive force between molecules of the same substance. So when you have two atoms of the same thing, or two molecules of the same compound, and they are attracted to each other, that is what we call cohesion. They co-adhere to each other, or cohere. So cohesion is that force between them. Well, because of those hydrogen bonds, water molecules are very attracted to other water molecules. So therefore, you are going to have a lot of cohesion in there. Now, water's hydrogen bonds makes that a very cohesive substance. Surface tension is the result of this cohesion. So if you're not familiar, surface tension is what causes water to kind of form bubbles. Like if you ever had a spoon and you fill it with water and it makes that nice little bubble, do that with some rubbing alcohol sometime, and you'll notice that it doesn't make a nice little bubble over the top. It's actually pretty close to flat across the top of your spoon. The water forms this little bubble over it because the water molecules at the surface are so much attracted to each other that they kind of keep the water together and kind of hold it in. This is what allows insects to walk across water, even though they don't break the surface tension. You can float a needle in water, and you can do that because even though the needle is more dense than water, its weight can't break through the surface tension or the cohesion of the molecules of water. So cohesion is a rather important property of water as well. Now, polarity is not because of hydrogen bonding, but the polarity of water is a very important property of water. See, molecules that have a slightly positive side and a slightly negative side due to unequal sharing of electrons in their covalent bonds are polar molecules. Well, water has hydrogen, which is not very electronegative, and oxygen, which is extremely electronegative. So you have a very polar bond between hydrogen and oxygen. Water also has two lone pairs of electrons, two pairs of electrons on that oxygen that are not bonded with anything. And so those two extra electrons also cause the oxygen side of the molecule to be very much negative and the hydrogen side of the molecule to be very much positive. It is a very polar molecule. So just like we see here in this picture, you see that the numbers that are giving us the electronegativities and the draw and the pull of those electrons. And so you have a very negative side because of those extra lone pair of electrons, and a very positive side because of the unequal sharing. Polar molecules are a very big deal in solution chemistry. So the unique properties of water that not solely because of hydrogen bonding can be explained because of its polar nature. So all those things we talked about that were about the hydrogen bonding causing these properties, not all of them are explicitly and expressly because of hydrogen bonding, but those other unique properties can be explained because of the polar nature. So water can dissolve a large number of substances. Now, as a very polar substance, water can dissolve most any other polar substance, as well as most ionic compounds. Not all, but a lot. Adhesion is kind of like cohesion. Cohesion is the attraction of molecules of the same kind, the same type, the same substance. Adhesion is the attractive force between molecules of different substances. Because of the polar nature of water, it's so positive and so negative on each side. When it comes close to something that's not, its polar nature will actually temporarily polarize the substance it's near. And so the negative side of the molecule will actually push electrons away from it and cause it to be slightly temporarily polarized. We call it an induced polarity. And so it causes the water molecule to then be attracted to it. That is what adhesion is. It's the force between molecules of different substances, and that polar nature of water kind of causes that. It gives an induced polarity to other substances. Now, adhesion is responsible for capillary action, which is when water gets drawn up into a straw, or when you take a paper towel and you stick it in water and the water kind of climbs up the paper towel. That's kind of what capillary action is. It's also one of the things that allows water to travel up the stems of flowers. It's not the only mechanism for traveling up. There is a limit to how far capillary action can take something, but it can climb up small tubes and stuff and through what is called adhesion, the capillary action. That's also where we get the word adhesive, and that's what an adhesive is something that sticks two things that are different together, like tape or glue. So water is easily the most important molecule to life, right? Our bodies are approximately 70% water. The Earth's surface is covered by approximately 75% water. Nearly all of the chemical reactions inside living organisms occur in water solutions. And without the water solutions, they won't occur, which is why your body ceases to function properly if you get dehydrated. If you don't have enough water, the chemistry that makes your life possible doesn't happen quite right. Water's very high specific heat helps regulate Earth's climate. Because water takes a lot of energy to change its temperature, it also holds a lot of energy. And so that's why we have the moving hot and cold masses of water in the ocean kind of help regulate Earth's climate. The fact that solid water is less dense than liquid water and therefore floats maintains ecosystems in the winter. Think about it for a second. If you've got a pond that is not super deep, but there's fish and stuff living in there, if water was like everything else and its solid form sank, then whenever the water at the top would freeze, it would sink And so water, as it got really, really cold, you would have situations where it would freeze from the bottom up because it would freeze and then sink, and then the next one would freeze and then sink, and so you'd have this sinking layer, which means all the stuff living in that pond would get frozen. But the fact that water freezes and ice forms on the top and the ice floats, it floats up there on the top of the surface, leaving liquid underneath it. So it freezes from the top down instead of the bottom up, which means that all of those things that are living in there can stay living, because ice is also, because of that specific heat, ice is also a pretty darn good insulator of heat. So once you have a thick enough layer of ice, the stuff underneath it is going to stay liquid and keep the animals and life that's living in the pond alive. If ice did not float, that would not happen. So the fact that it is less dense is very important. So this is actually why all these important things about water to life, this is why when scientists are looking for life in other places of our solar system and throughout the galaxy, they're looking for life, they're looking for water, because as far as we know, life cannot exist without water. So we look for water or evidence of water so that we can find evidence of other life somewhere else. That's what they're looking for. Whether they'll ever find it, who knows? So that brings us to our discussion of solutions. So what is a solution other than the answer to a problem? That's a completely different use of the word, but when we're talking about solutions in chemistry, a solution is a homogeneous mixture consisting of two or more substances in which one substance dissolves another. So one substance is dissolved in another. So you can have 2, 3, or 4 things dissolved in something else, but you're always going to have, and that's the way we talk about it, is something is dissolved in something else. If it is dissolved in something, then you're dealing with a solution. Because it is a homogeneous mixture, it is impossible to tell the substances that make it up simply by looking at it. So now let's talk about some terms that you need to know. And this is going to get a little confusing to some people because so many of these words start with the same 3 letters. We're dealing with solutions, and so if you don't learn this vocabulary that all starts with SOL, well, if you don't learn the vocabulary, you'll end up being SOL. So let's not get that way, and let's learn some of these vocabulary terms. So solvent. The solvent is the substance that is doing the dissolving. So when you put something in water and that something dissolves, water is doing the dissolving, so water is the solvent. The solute is the substance that gets dissolved. So if I put salt in water, the water will dissolve the salt. So the salt is getting dissolved, so your salt is the solute. Soluble describes if a substance can be dissolved in another substance. So salt, or sodium chloride, is soluble in water, but sand is not soluble. If I put salt in water, salt will dissolve. If I put sand in water, sand just sinks to the bottom. It doesn't dissolve. So sand is not soluble. It is insoluble. So some things may not be soluble in water, but they'll be soluble in something else. For example, cayenne pepper is not soluble in water, but it is soluble in oil. So whether or not something is soluble does depend on what solvent you're talking about. Most of the time, most always in chemistry, we're using water as our solvent. Not always, but most of the time. Solubility sounds a whole lot like soluble, all right? And you could break it down as the ability to be solvated. So soluble means will it dissolve. Solubility is how much can I dissolve. So salt and sugar will both dissolve in water, but salt will dissolve a whole lot more. You can get a whole lot more salt to dissolve in water than you can sugar. So salt has a higher solubility than sugar does because you can dissolve both of them. They're both soluble, but the solubility is all about how much can I dissolve. Some things you can dissolve a little bit and that's it. Some things you can dissolve a lot. All right, so that's what solubility is. So if something is soluble, it will dissolve. If it has a high solubility, you can dissolve a lot. You can have something that is soluble with a low solubility. It will dissolve. It just doesn't dissolve very much. Dissolution, also sometimes called solvation, is the process of dissolving in which solute particles surround, or solvent particles surround solute particles. So this is the process of dissolving, is called dissolution or solvation. I like the word solvation a little bit better because it's the solvent is surrounding your solute, and so it's being solvated, right? Aqueous is a word that we use to describe a solution in which water is the solvent. We talked about this very briefly in another video a long time ago, but aqueous, water involved, aqua, all right? Aqueous means water is the solvent. Most everything that occurs in our bodies, most of the chemistry that we do in our labs, a lot of the chemistry that we do in general is aqueous solutions. So oftentimes you'll actually hear people talk about something being an aqueous solution. We're going to have an aqueous solution of salt. Well, that means we have salt dissolved in water. Aqueous means dissolved in water. Concentration, other than just your ability to focus on something with your brain, that's not what we're talking about here. Concentration is a measure of how much solute is dissolved in a given amount of solvent. So if I have a little bit of solute, if I take a teaspoon of salt and put it in a gallon of water, I've got a solution of salt water, but it's a very not highly concentrated solution. Now, if I put 5 pounds of salt, if I put 5 pounds of salt in a gallon of water and dissolve it, it's going to be very concentrated. It has a lot dissolved. So concentration has to do with how much is dissolved. Solubility is how much can dissolve. Concentration is how much you actually dissolved. We'll talk more about concentration in a couple of videos. Now, dilution is the process of adding more solvent to a solution to decrease its concentration. So if I have a little bit of a little bit of solute dissolved in a solvent, then I have a low concentration. It is a diluted solution. Now, if I add a whole bunch of solute and get it to be a really concentrated solution, then in order to get it to be diluted again, I have to dilute the solution. And so I go through the process of dilution. And dilution is adding solvent so that you will change its concentration. And again, we will talk more about concentration and dilution in another video in the future. Now, there are different types of solutions. So we've talked about what all these words that go with it. So we've got solutes and solvents. And so there are different types of solutions that are kind of dependent upon what your solvent and your solute are. So most solutions that you think of and most solutions that we usually use are thought of as liquids. But solutions can be gases and solids as well. A solution just has to have a solute dissolved in a solvent. It does not have to be a liquid. That's very important that you understand that. Right? The state of matter of a solution depends on the state of matter of its solvent. If your solvent is a gas, it's going to be a gas solution. If your solvent is a liquid, it's going to be a liquid solution. If your solvent is a solid, it's going to be a solid solution. We're going to talk about different situations where these could all come into play. So a gas-gas solution usually refers to a mixture of gases. It means we have a gas that is dissolved inside of another gas. All right, air is a good example of a gas-gas solution. Air that we breathe is approximately 73% nitrogen and about 23% oxygen, and then there's some other gases in there also. But our normal air that we breathe is mostly nitrogen. Now, in this case, nitrogen is considered the solvent because it is the most abundant of the chemicals there. So nitrogen is the solvent, and therefore all of the other gases are the solutes. Now, oxygen is the second most abundant, so it's the most abundant of the solutes, but it would still be considered a solute in the breathable air. Nitrogen is the solvent because it's the largest percentage. A liquid gas solution is a solution in which the solvent is a liquid, and the solute is a gas. So notice the terminology there. Liquid came first, so it's the solvent. Gas is the solute. So it's a solvent solute solution. So a liquid solvent, a gas solute. All right. So you have a solvent that is a liquid, a gas that is a solute that is a gas. All right. Example there would be carbonated water, like in sodas and stuff like that. Water is your solvent in carbonated water, and carbon dioxide is the gas that's dissolved in there. That's actually what makes it bubble, is whenever the carbon dioxide comes out of solution, you get the bubbles. You also have liquid-liquid solutions, where you have a liquid dissolved in another liquid. So you're going to have one liquid that's a solvent, and one liquid is your solute. Just like with gases, it depends on which one's the largest volume there. Antifreeze that you put in your car is a very good example of a liquid-liquid solution. Your solvent is water, and the solute is another liquid, ethylene glycol. And so you can mix those together in different concentrations to get different uses for your antifreeze. Usually they're mixed together in a 60-40 or a 50-50 relationship, but water is usually your solvent, ethylene glycol is the solute. Then you can have a liquid solid solution. This is one where we have a liquid solvent, like water, and a solid solute. All right, so salt water is a really good example of that. Water, again, is your solvent. It is a liquid. And your solute is salt. Sodium chloride is a solid. A solid-solid solution, usually referred to as an alloy. A lot of people get confused by this, but a solid-solid solution is a solid solvent and a solid solute. So you have two solids that are dissolved together. How does that happen? Well, an example would be steel or any other alloy, brass, bronze. These alloys are solid-solid solutions. Right? So in steel, iron is the solvent. It's the most prevalent. It's the one you start with. You have iron as your solvent, and in the iron, we dissolve in carbon. Now, there's a bunch of different ways to get this to happen. Usually, you would actually, to make your steel, you would melt the iron to a liquid form, dissolve the carbon in it, and then let it solidify. But you can actually force the carbon into it just when it's not a liquid. You just have to get it hot. All right, then there's something called electrolytic solutions. This is not really necessarily about the type of, the state of matter of the solute and the state of matter of the solvent, but an electrolytic solution is an aqueous solution, so water's the solvent, in which the solute is an ionic compound that ionizes, which means when you dissolve it in water, the ions in that ionic compound break apart to make their positive and their negative ions. And when you break them, when they break apart, they ionize, they separate from each other in solution, and they have these charged particles floating around. It then conducts electricity. So that's what an electrolytic solution is. That's actually a lot of the liquid in our body is an electrolytic solution, and that's actually how our brain impulses, nerve impulses, muscles, and all that stuff, they work off of electrical impulses, and that only works because our bodies conduct electricity, and they conduct electricity because of the high number of electrolytic solutions in our bodies. So lemon juice is a really good example of an electrolytic solution. Lemon juice, or the thing that gives it its tartness, its main component of lemon juice is citric acid, where water is the solvent and sodium citrate is the solute. That's what citric acid is. And so lemon juice will actually conduct electricity. Sulfuric acid is a very good electrolytic solution. That's actually what's inside of a car battery, and that's what allows the electricity to work. So we've gone through quickly the properties of water. We've gone through the vocabulary and why the properties of water exist. Hydrogen bonding and polarity are the main reasons for water's very unique properties, but these unique properties of water lead to it being a very good solvent. And in our next video, we're going to talk more about solubility and how things actually dissolve in the solvation process. So Go back through and make sure you learn the vocabulary, all those SOL words. Make sure you learn them and know what they are so that whenever I use them and when we talk about them, you're going to understand what I'm talking about, because I'm going to use those words and I'm probably not going to define them again. We're just going to use them as they are meant to be used. So hopefully you understand the importance of water to solution chemistry and the basics of the different types of solutions. Thanks for watching and have a day.